Live from Norwich with the best of the fest, the Naked Scientists.
Hi, it is Dr. Chris, that's me, and Dr. Dave is here to help present tonight's programme too. Hi, Dave.
Hi, Chris.
We are live here at the University of East Anglia in Norwich, which is playing host to this year's BA Festival of Science. Now, the BA is actually the largest science event to take place in the UK, and the idea here is to showcase some of the great science that's going on around the country. Now, we'll be here every evening this week, as Nick says, with a roundup of the best of the fest, some of the highlights of the day.
We have a lowdown on life at the BA Festival with Anna Lacey. We have two guests here tonight. We've got Bristol University's Bruce Hood on the science of superstition. We have Birmingham University's Claire Davis on how to make athletes jump faster, jump further, run faster in the Olympics. And if you're in an experimental mood, we have Kitchen Science with Derek, Sebastian and Sam in Ecton Brook in Northamptonshire, where you can learn how to build a fire extinguisher.
Yeah, and after 8 o'clock, of course, we'll be handing back to Nick in the studio in Norwich at the Forum for a science phone-in. So if you'd like to talk to us about any of the issues that we've raised in tonight's programme, you'd like to ask Bruce or Claire a question about what they're going to be talking to us about, the science of superstition or the science of sport, or you'd just like to ask us a science question, then get phoning in now or throughout the programme for the next half an hour. The number to call, 0845 30 50 007. That's 0845 30 50 007. The lines are open now. Now, Dave, what have you been up to today?
Well, I was listening to David Richardson at University of East Anglia here. He studies bacteria, and he was looking at bacteria who are involved in the nitrogen cycle. This is nitrogen. It starts off in the air. 70% of the air is nitrogen, and then it gets fixed. It gets turned into nitrates by bacteria and sometimes by lightning. And plants take it up, they use it as fertilizer, and eventually, normally it gets broken down back into normal nitrogen, back into the air. How sometimes, especially if you put lots of nitrate fertilizers down, it gets turned into a gas called nitrogen oxide, NO.
Nitrous oxide.
Nitrous oxide, thanks, Chris.
Laughing gas, that is.
Yeah, it is.
When you break your leg and you go to hospital, that's what people give you to make you feel happier. It's a very good painkiller.
They always used to use it as an amusement. It was a major thing in the 19th century. People go and breathe the stuff. They thought it was great fun.
But what's the importance of the fertilizer?
Anyway, the problem is that nitrous oxide is also a very powerful greenhouse gas. It's 300 times worse than carbon dioxide, and apparently it's making up 10% of global warming, and it's going up at about 2.25% every year. The problem is it lasts for 200 years in the atmosphere, so what we put in now will still be here in 2200.
So one spin-off is that people will be happy about climate change. I suppose happier about climate change because there'll be lots of nitrous oxide in the atmosphere. Is there anything we can do about it?
Basically, be much more careful about how we fertilise fields, and don't fertilise everything with nitrates, only things which need it, so they'll get taken up quickly by the plants and not produce large quantities of nitrous oxide.
It was interesting, staying with the sort of bug theme for a second, I got chatting to Glenn Gibson from the University of Reading, and this guy's amazing. He's very interested in probiotics and prebiotics. In other words, the kind of drinks that you can buy that will have you rolling down the aisles of supermarkets doing cartwheels and things that allegedly improve your health. He's interested in finding out whether they really do have a beneficial effect, and also how things that you can eat can influence the bacteria natively and naturally growing in your intestine. They're called prebiotics. And in fact, if you like porridge, Dave, I'm sure you eat porridge every day to get your oats, then that actually contains a lot of a substance called beta-glucans, and they encourage the growth of good bacteria in the gut. But to find out whether these things really have any beneficial effect, what Glenn Gibson has done is to build a whole load of models of the intestine, not just to humans, but cows, sheep, rabbits even, in his laboratory. He says it smells quite a lot, and it's actually a whole system of tubes and pipes and glass fermenters, and it's all pushed through by pipes and filter papers. And I said, can you give this machine diarrhea? And he said, well, yes, you turn the pump up a bit high, you can. But allegedly it has actually enabled him, by taking bugs out at various stages of his model, he can actually work out exactly what happens to your dinner as it goes down, how the bugs influence that, and how those bugs grow and respond to different things that you have in your diet, including antibiotics that doctors like to dish out.
I was also listening to a guy called Nigel Allinson, who's at Sheffield, and he's developing also about fingerprints. The problem with fingerprints at the moment is that they take there's burglar burgles your house, they take the fingerprints, they put them on a bit of paper, they put them in the van, they forget about it for a couple of days, they eventually take it back to the police station, they have to send it off to the lab, they scan it, and about between 3 and 18 days later they actually get an identification back.
So how are they going to speed it up?
Well, his idea, and what he's been doing, is he's basically give all the policemen a laptop.
Sounds nice. I'll be a policeman if you get a laptop.
and then they scan the fingerprints at the crime scene,
Yep.
and then they want to send it back to the base. The problem is that fingerprint would normally they want to send it over mobile phones, so you get lots of coverage, and the police network won't take data. And it would take about 40 minutes to send it, and that would be a bit slow if you had like 15 or 20 fingerprints to take. So he's had to use data compression.
So making the file smaller, so it takes less time to send.
Yeah, like all files on the internet are normally JPEGs. The problem, he first tried JPEGs. The problem is they do all sorts of strange things to the image.
So you get a blurry fingerprint, basically.
Blurry fingerprint. And the really bad thing is it puts lots of extra edges on there which weren't there before.
Is there a way around it?
Well, he uses a special, newer, much more modern thing called JPEG 2000, and you can get its fingerprint down in about 1 to 4 minutes, and it takes 2 hours to get identification in Lincolnshire now.
Rather than the ridiculous time it would have done before. Well, this year is, of course, the 175th anniversary of the BA, or British Association, as I said. It's originally set up, the BA, to help scientists and the general public to talk and interact with each other about important scientific issues. But what's it really like to come to a festival like this? Because they're trying to get members of the general public to come in and to actually experience a bit of science and to come into contact with scientists. But it's often difficult if you don't have the chance to go to get an understanding of what it's like on the ground. So to find out, we've got our Naked Scientist reporter Anna Lacey out there to give us a unique flavour of the festival.
I'm here on campus at the University of East Anglia, and so thought I should check out some of the action here. So I started my quest in the canteen, where I got chatting to a couple of visitors over a few poached eggs. BA Festival veteran Alistair told me why he comes back year in, year out.
I've been coming to the festival for several years now. My background's actually in physics, but the great thing about the festival is it lets me find out about all these other parts of science outside my specialism.
But on the other side of the table, eating beans, toast and a sausage, Horace from Tyneside told me why he's boycotted science festivals in the past.
They were pulling the content out and substituting bangs, whistles, puffs of smoke and bad smells. And of course, if you're not really interested in science, you're not going to be interested because someone does fireworks. What matters is showing how interesting science, just like the arts and everything else, really is, and helping people to find the potential for interest which is in them.
So what are they off to see today then? Here's Alistair again.
Well, I should be going to the Antarctic one this morning, finding out about climate change.
Are you concerned about climate change?
Well, I think everybody's concerned about climate change. I think there's plenty of evidence that there is change of sorts, but whether it's going to be quite as dramatic as some of the people are telling us, I don't know.
Well, I get the distinct impression from the BA that the scientists here today are meant to be answering questions like this, so I went on the hunt for some answers. The scientist who came to the rescue was Eric Wolfe from the British Antarctic Survey in Cambridge. One of the ways to study climate change is to look at the gas concentration in ice cores, which acts as a sort of timeline for carbon dioxide levels. I asked Eric what they tell us about climate change and how far back we can travel back in time.
In ice cores you can go back so far 800,000 years, and what we find is that over the last 800,000 years carbon dioxide has gone up with the climate each time, so every time it's warm there's more carbon dioxide. And perhaps the most striking thing is that in the last 200 years the rate of increase is about 50 times faster than anything we see in the natural record.
Well, we've been hearing this and similar bleak outlooks from scientists for years, but the problem hasn't gone away. Frances Cairncross, the president of this year's BA, is hot on climate change and has made it one of the themes for the festival. I asked her what she suggests as a solution.
I want to see, for example, economists involved and sociologists and political scientists all involved in the understanding of climate change and how to respond to it. I think there's a real contribution here and with lots of other problems if scientists and social scientists can work together.
So it seems from that as though Alistair will have to wait with the rest of us for an outcome on climate change. But in the meantime, I asked Frances what she thinks is going to be the highlight of the festival.
Well, there are lots of wonderful speakers here, of course, but for me the very best thing of all is a young woman at the top of the main flight of stairs on the campus selling marvellous homemade Norfolk ice cream. It's to die for.
That was our Naked Science reporter Anna Lacey. More from Anna tomorrow, where she will be out and about around the BA Festival of Science here at the University of East Anglia. Now, joining us in the studio this evening is Professor Bruce Hood, who has joined us from the University of Bristol, and he works on the science of superstition. Hi, Bruce.
Good evening, Chris.
Now, do you find that people don't take you seriously when you say I work on why people are superstitious about things?
On the contrary, I think it's something that's intuitively appealing to most people to know if there is any science behind magical beliefs.
What sorts of things are we talking about when we say the science of superstition? I gave the kind of description of a wedding ring earlier, But what other things is, I suppose, walking under ladders and stuff as well?
Yeah, in general, it covers any phenomenon that appeals to invisible forces or mechanisms that are categorically denied by conventional science. So that's a wide remit of phenomena.
So how do you test this? Talk us through your research to actually test what people do and how they're superstitious.
Well, I'm a developmental psychologist, so I study children and the way that children reason about the world. And so I started off by investigating how they thought about the physical world and the nature of their toys and what special attributes they gave to their toys. And I soon discovered that they treat these as special objects which have unique characteristics and almost have minds. And this led me to think that actually the way that we treat sentimental objects as adults is very similar. So, for example, I noticed you wearing a wedding ring, and you probably would be very reluctant to take an identical duplicate because you think that your original
but
has...
Bruce, this is an identical duplicate.
Oh.
And the reason I can tell you that is that on the third day of my honeymoon, I was swimming in the Mediterranean with my wife, and I was demonstrating at night time the phosphorescence when you make the water move very fast and the animal microorganisms emit light. And I was lucky enough to see my wedding ring then disappear down in the most spectacular trail of phosphorescence down towards the bottom of the sea, and I could never find it because it was a gravelly bottom. And we nearly got into trouble because there's my wife standing on me, holding me on the bottom underwater as I went across the seabed with my fingers, and lots of people thought she was trying to drown me.
Oh, well, that's an amazing story. Luckily it happened during the honeymoon, so you've had sufficient time to make up for it.
I have got another one, but go ahead. Why do you think actually that people do become attached to the fact that, you know, I have this gold ring and this one is important to me? If you gave me an identical replica, I would think, I prefer the original one. Why do we have in our brains this tendency to that behaviour?
I think this derives from what we call in the field essentialism, the idea that each of us has an inner soul or an essence, if you like, that defines who we are. And this is the way that we think this can inhabit the body and also transfer over into objects and artifacts that are associated with people who we care about. In the same way, we can be reviled or treat objects associated with evil people as being disgusting. So I demonstrated that today in my talk.
Yeah, go on, tell us what you did, because people will be shocked to hear this.
It was shocking, but I think it was a very powerful demonstration of the power of intuition. So I asked whether or not the audience would be prepared to wear a cardigan, a second-hand cardigan.
It would look like quite a nice cardigan from a distance.
Indeed, it was cashmere. But it was clean, and about half the audience said they were happy to do so. And notably, they were more happy to do so when I offered them £10. But then when I told them the cardigan used to belong to Fred West, the sadistic killer, of course the hands shot down immediately. But interestingly, one person still had their hand up, but then the rest of the audience moved away from them. So I think it's a very powerful kind of social mechanism.
But the fact that children do it argues that it must be printed into us genetically in some respect, or where do we get this behaviour from in the first place, and why? Why do we need this kind of behaviour?
Well, the brain builds models of the world. It tries to figure out what's going on, and a lot of that model building means thinking about things that you can't necessarily see. So essentialism, children from about 2 to 3 years of age think that there's something or an essence inside living things like animals that make them what they are. So it's part of a natural reasoning mechanism that just gets overextended into the supernatural.
And where are you going to head next with this? What's sort of on the wish list next to try and crack?
Well, we're now looking at adults who claim to be rational, and we recently started some work to demonstrate that they actually behave irrationally if they see their beloved object being destroyed or presumably being destroyed. So at one level they can be kind of very sensible about the whole thing, but at a kind of latent unconscious level they're really still thinking like children.
Thanks very much, Bruce. That's Bruce Hood, who's from the University of Bristol. He's going to hang around here and remain with us after 8 o'clock. If you'd like to ask him any questions about why people shouldn't walk under ladders and that kind of thing, and is there any evidence that you shouldn't, then give us a call. We're taking phone calls now, 0845 30 50 007. Also here in the studio with us is Claire Davis from the University of Birmingham. Claire, hello.
Good afternoon.
How are you going to get our athletes winning in Beijing?
Well, it depends on what sport. In some sports where engineering technology can have a big effect, then research and development at universities, companies, within governing bodies can give our athletes a competitive advantage.
So you work at the University of Birmingham. You do research on materials to make people run faster, jump higher, that kind of thing. So what kind of things have you worked on recently?
We've within the materials department at Birmingham, we've got people, myself included, who work on golf clubs, so trying to optimise performance to allow golfers to hit the ball further or with greater accuracy. Safety elements, so crash helmets, cycling, so lightweighting bicycles, things like that.
Now, can you answer a long-standing conundrum for me? Why do you need dimples on a golf ball?
That's not really materials. It's aerodynamics.
Well, it is a material, isn't it? It's a plastic.
Yes, but it's about design. It's
Okay.
aerodynamics. So you have the dimples to change the airflow over the ball and to optimise the distance. But there's a lot of rules and regulations about what type of dimples, what size they can be.
Really? So how does it make a difference?
It affects, as I said, airflow. Air flows across a body in two fundamental ways, either turbulent or smooth flow, if you like. And if you change those, you change the way the ball flies through the air and the distances that can be achieved.
But golf's quite an old game, isn't it? So how long ago did someone suddenly decide that they could improve the aerodynamics of an object, like a golf ball?
Well, with most things, that however long ago we go, then there's always continual advances. So golf is just one example. You had solid wood heads for drivers, whereas nowadays we have what we call oversized drivers, hollow metal heads. And so it's all mostly incremental, but as you go through history, you find that we're constantly playing around with these things and improving them.
I was going to say, I know a few people with a hollow head. No, Dave, go ahead.
Do you find that you end up in a sort of competition with the regulatory bodies who are trying to limit how much you improve things, and then you try and get around the rules all the time?
It doesn't have to be competition. Sometimes we find that it's the regulatory bodies that are coming for the research and development. So, let's take tennis for an example. The developments within tennis has meant that the racket heads have become larger, the power of the rackets become very significant, and people were complaining, well, it's not an exciting sport anymore, it's too serve dominated. You saw hardly any rallies a few years ago at Wimbledon. So the regulatory bodies was, well, we want spectators to enjoy the sport, we want the athletes, the players to enjoy the sport. So they went forward for research and development. Some of this was done at Sheffield University, to how can we slow the game down? It's an odd concept, isn't it, slowing something down? And that was all done by changing the balls. So you can make a ball
bigger
slightly
balls.
bigger.
On the bigger now.
Bigger
Yeah.
balls.
So there was a good old headline in one of those fantastic red top papers that said, tennis players are getting bigger balls.
But not all the time.
No.
That's the great thing. You can have your bigger balls when you need them. So Wimbledon, a very fast surface being grass surface, you can use your bigger balls. But on the continent, where it's clay court, they don't need them.
Now let's talk about pole vaulting for a second, because that has shown enormous evolution, hasn't it, in very recent times actually, because isn't that actually ancestrally a game from Holland?
It is. We believe that it originated with dike jumping. So
It sounds rude, actually.
It does indeed. But the Dutch farmers, getting across their fields and across the dikes. But that would have originated with what materials were at hand. So nice solid wooden poles, ash, hickory, things like that.
But how far would someone have been able to jump with a solid lump of hickory?
Well, it would have been dictated by how long the pole is and how wide the dike is as to how far you need to go. Most of it there would have been done by distance, and it's only as you start showing off you go for height. And so for height and for distance, the dike jumpers would climber up the pole, and it's only really when it was becoming a sport that in America they banned hand movement, so you can't climb up the pole to give you extra height. But then we saw sort of naturally engineering materials, bamboo, hollow material, good stiffness being used, and a brief flirtation with using metals, so aluminium and steel.
Steel?
Can you imagine it running down the runway with this equivalent to a piece of scaffolding pole?
And how far would people have been able to jump with that?
They were getting, for height, about 4.5 metres. So it was reasonable heights. But after that, very short period with metals, they started using glass fibre composites, and that changed the sport, and we got huge increases in, for example, world records and Olympic records.
So how was that improving things? Was it storing energy, while you in the rod, which would make you higher or something?
Yeah, you're quite right. It changed the style because the poles are now flexible. And so instead of them being these solid, rigid poles, they can now flex, and that allows the athletes to run very fast, bend the poles as they plant them, store the energy. Then as the pole straightens out, it gives the energy back to the athlete. They now go upside down, vertically upside down, feet first, up over the poles. And we're now at world records for the men of about 6.12 metres. Big, big changes.
Thanks very much, Claire. Claire Davis is here in the studio with us, and if you'd like to ask her any questions, perhaps you wanted a bit of dike jumping, 0845 30 50 007. It's time now for the first of our special kitchen science experiments. Every night this week, our kitchen science team will be paying a visit to a different kitchen somewhere around the region. Derek Thorne and our own Dave Ansell went to see Sam and Sebastian in Ecton Brook in Northamptonshire to find out how a fire extinguisher works.
Hello there and welcome to Ecton Brook in Northampton. We've come here for the week's first science experiment, and remember, you can do this at home, so please do listen out for all the things that you will be needing. With me is Dave, my colleague, who has set up the experiment today. So Dave, what are we going to be doing?
Well, this evening, Derek, we're going to be making a homemade fire extinguisher.
A homemade fire extinguisher, fantastic. And also we have some wonderful helpers here. Guys, tell us your names and ages, please.
Hi, I'm Sam and I'm 9 years old. I'm Sebastian and I'm 9 years old as well.
You're 9 as well. Excellent. And you guys do science at school. Sam, what's your favourite thing about science?
Well, I like doing experiments.
Great stuff. And yourself, Sebastian?
I don't like experiments, so I'm putting my hands up, but I hope I'll have good fun.
And I think we're going to convert you today, because this experiment's going to be very, very cool. And so, you at home as well, you can do this experiment. It's very, very easy, and it is great, I assure you. Basically, all you need is a pint glass, you need some bicarbonate of soda, some vinegar, a sufficient quantity, like a cupful or something like that, and a candle and something to light it with, and also a teaspoon to measure things out. And I think that's about it. So, Dave, what do we do with all these things?
Sam, could you take 3 or 4 teaspoons of bicarbonate of soda and put it in the pint glass?
There's 1, there's 2, there's 3.
That'd be great. Now, the next thing you should do is pour about 1.5 centimetres of vinegar over the top of them. It'll also work with lemon juice or anything like that.
So Sebastian's doing this now. And what's happening, Sebastian?
Oh, it's going fizzy.
OK, then.
A bit more in, I think.
Right, we're going to put a bit more in, because we want lots of bubbles here, guys, OK?
Wicked. It's going to overflow.
Oh, and it's just overflowed a little, but we've got lots of bubbles there, so that's looking very healthy, isn't it, Dave?
That's exactly what we want to see, that's right.
OK, so we've put some vinegar, glugging some vinegar there onto the bicarbonate of soda in the pint glass, lots and lots of bubbles, and then what next?
OK, so I'm now going to light the candle. Now, Sam, could you pick up the glass and now pretend it was full of water? As if it was full of water, can you pour it onto the candle?
Oh, what happened?
It disappeared. The fire on top of the candle was demolished.
Demolished, yeah. The flame went out, didn't it? Yeah. Sebastian, what did you think happened?
I thought because the vinegar is really cold and sparkly, it made the fire go out.
Well, we've got Dave here, who is the man with the explanations all the time, so he's going to be telling you what is actually going on there. So Dave, what's happening?
Well, first off, why does it fizz? Well, locked up inside the bicarbonate of soda, there's a gas. Have you ever heard of carbon dioxide?
Yeah.
Yeah, what's carbon dioxide?
It's the special air.
It's a kind of air, it's a kind of gas. It's a kind of gas which you breathe out. Now, locked up really tight in the bicarbonate of soda, there's this carbon dioxide, OK? When you add vinegar, which is a kind of acid, and so is lemon juice and things like that, if you add that to bicarbonate of soda, it fizzes lots. I don't know if have you ever eaten sherbet, which fizzes in your mouth? OK, that's got bicarbonate of soda in it, and the fizz is exactly the same as this. Now, carbon dioxide is heavier than air, so instead of just like floating out of the glass, it will just sit at the bottom of the glass, a bit like water in the glass. But it's invisible, so you can't see it. Now, when things burn, OK, they take in fuel, they've got fuel, and they take in something called oxygen, which is a gas which you breathe in.
And you guys have heard of oxygen as well, have you?
Yeah.
And they turn it into carbon dioxide and maybe some water as well. So if you pour carbon dioxide onto a flame, it's like pouring its waste product onto the flame. So it's a bit like you eating wee.
Can you guys imagine living on wee? That's your waste product. I agree, absolutely. So really then, the flame needs oxygen. It can't live on carbon dioxide, but you pour carbon dioxide on it, just can't stay up, can it?
Yeah, it'll just go out.
OK, fantastic. So we've just made a homemade fire extinguisher then, have we?
Yeah, some of the fire extinguishers are basically a cylinder of carbon dioxide which is compressed down really hard. They tend to be the ones with a little horn on the end. And if you press the lever, it just squirts out carbon dioxide all over the flames that will put them out.
OK, and so what other kinds of fire extinguisher do we have?
Well, there's also powder fire extinguishers, which are actually made out of bicarbonate of soda as well.
Oh, so we can make another fire extinguisher here, guys.
So, yeah, we can make another. So if I light the candle again... Sam, could you take a little pinch of bicarbonate of soda? Yeah, that's right. Now put it onto the flame.
Hey, what happened?
The spark disappeared.
Yeah, so the flame disappeared.
Yeah.
So we've made another fire extinguisher, really.
Because another way to get the carbon dioxide out of bicarbonate of soda is heating it up. So if you throw bicarbonate of soda onto a flame, it will release all that carbon dioxide and it'll put the flame out.
OK, so, guys, you've seen some different types of fire extinguishers here. What did you think of the experiment, Sam, firstly?
It was clever.
Excellent. And, Sebastian, what about you?
I think I like experimenting now because it's so fun.
So you're a convert. You like science now?
Yeah.
Oh, well, that is fantastic. So there you go. Thanks to Sam and Sebastian from Ecton Brook in Northamptonshire, and also to Dave, who set up the experiment. And do tune in tomorrow as well, because we've got another kitchen experiment, which you can do at home. We'll actually be in Downham Market playing around with some red cabbage, so listen out for that. Until then, it's goodbye.
Thank you very much to everyone at Ecton Brook. And do please remember, if you are playing around with candles, do be careful. Now, that's pretty much our wrap for tonight. And for our festival update tomorrow, we'll be joined by Nick Wareham from Cambridge University, who'll be talking about diet and exercise and how it can influence our health in later life. And Nobel Prize winner John Walker will be talking about the science behind nanomachines, very tiny technology. Right now, Nick, it's back to you.
Thank you very much indeed, sir. So we'll be taking some questions, ask our experts about superstition and sports stuff. And let's bring Jim in. Hello, Jim.
Good evening, sir.
Good evening. You want to talk about this homemade fire extinguisher that Dave made?
Yeah, I'm getting on in age, but twice in my lifetime I've had the occasion to have a chip pan fire. And the usual routine, wet cloth over the top. Would this homemade fire extinguisher work on one of those things?
It would be dangerous. The problem with putting something which is going to produce lots of gas in a chip pan fire, and the reason why you really, really don't want to use water, is that if it gets under the fat, it's going to do the same thing as the lemonade bottle with the Mentos in it.
Oh,
it's
right.
going to basically produce a foam of hot, burning oil. And if I've occasionally seen this on Fire Brigade doing it with a 50-foot pole and putting a little glass of water into a chip pan fire.
Yeah, I've seen that done, yeah.
And you get, basically it produces a foam of burning oil and you get a huge explosion.
Because the water goes underneath the oil, because it's cold, and also because oil is less dense than water, so the water sinks to the bottom and then immediately vaporizes, as you say, and just creates enormous amounts of steam under the oil and blows it all over the place.
And using a carbon dioxide fire extinguisher is dangerous because the carbon dioxide comes out very fast over the one to the horn, and it will blow the oil around and produce a similar effect.
So that's why
the drawing board is best for the old wet cloth job.
Oh yes, it's the best way because the damp cloth keeps the temperature down so the cloth doesn't immediately burst into flames, but it also cuts off the supply of fresh oxygen, and that's what's actually fueling the fire. Because when the fat is confined to a tin, then there's only a small surface area, the surface area of the top of the liquid, in contact with any air, which is what it needs to burn. If you put the wet towel over the top, it cuts down the supply of oxygen. The waste products, the burnt products, the carbon dioxide as the oil burns when it reacts with oxygen, accumulate on top of the oil, and it just blankets the fire and puts it out.
Yeah, it was just a thought I had, but there's no panic because I got rid of a chip pan years ago. But
that's very good for your health, but that kind of kitchen science is to be discouraged, I think.
Yeah, OK, thank you very much for your help.
You're welcome.
Thank you, Jim. And I just want to bring this one very, very quickly. And that is the experiments, the kitchen experiments that you do are available online at bbc.co.uk/Norfolk, aren't they? Because you've done a whole load of them.
Yeah, the one we're doing this week, I've been video doing them, and you can see me doing them online.
That's right. If in fact, more generically, if you go to bbc.co.uk/lookeast, in the middle of the homepage, right at the top, is a link through to our speed of light experiment we did in a microwave last week. And in fact, a number of people have done very well at that, and some of them have got the answer nearly completely correct, because there's a Hall of Fame on our website. If you type in your results from the microwave experiment, then it will calculate the speed of light according to your kitchen and then enter your result on our website. And some people have got it nearly spot on, but I'm not going to say who. I won't give the game away quite yet and let people still have a go.
Let's go to Pat. Hello, Pat.
Hello, hello, Nick. Hello, Dr. Chris.
Hello.
You spoke to me for over an hour before. You're a grand chap.
Oh, thanks. Very nice.
When I was in the science class, 1900 freezing to death, the teacher, I can't remember the answer to this, he said fill a glass with water right to the very brim, put a bit of paper over it and turn it up the other way and the water won't come out.
And did you try it?
Yes, it worked. No, I don't know the answer to it.
Well, in order for the water to fall down, you've got to get some air up into the space which the water will make as it falls down.
Yeah.
And if you put a piece of paper over the bottom, the only spaces that the water can get out or the air can get in are very small around the edge.
Yeah.
Or through the little holes in the paper. And there's something called surface tension, which means that it's very hard to get water through a very small hole, and water will actually... you've got to make more surface as it goes through the hole, and it will actually fight you.
Yeah.
And that's strong enough to hold back the weight of the water in the glass, and so it will sit there.
And, when I was at school, we discovered this really good trick to get the... it was a bit nasty. It's a typical schoolboy thing to do to the cleaning ladies. But what we found is that if you take a cup and saucer and fill it with the rather rubbish cups of tea that you get in school canteens, and then you put the saucer on top of the cup and turn it over, you can play the same trick. And what the staff think is that it's an empty cup, and they'll just pick that up and put it back in the kitchen. And, of course, as they pick it up, the whole thing explodes all over them. Cold manky tea. It was great, very, very, very funny until we got caught doing it, and then we got punished. And, Anyway, sorry, a little aside there.
Right, thank you.
Thank you very much indeed. Cheers, Pat. Quick question for Bruce. Jim wants to know why people don't walk underneath ladders.
Bruce, what do you reckon?
Well, it's probably one of these cultural superstitions. You just don't want to chance fate. People assume that it comes from experiences, and therefore they buy into this as a general principle. I suppose that's the best explanation. Interestingly enough, though, if you ask people about walking under ladders, and they say rationally that they would be quite happy to do so, quite often when they don't think they're being observed, they go back to avoiding the ladder. So we can sometimes override our superstitious behaviours.
I sometimes make a point of walking under ladders on purpose, just to show that I'm not superstitious.
I guess there is actually some basis behind it, because if there's someone up the ladder, they're quite likely to drop things.
Yeah, there's a very good practical reason why you shouldn't walk under a ladder as well.
But people do it even when there's no one up the ladder.
Yeah.
Now, what is it about the sort of smell associations? Because I guess that the science of superstition and was wanting to hang on to things and our kind of conservatism is all wrapped up into one neat package in terms of our senses. And I know that the sense of smell is a very, very strong factor in this, isn't it?
Well, you might be referring to the idea that certain smells evoke very early memories. And is that what you're referring to?
Yeah.
Yes, well, memories are stored in a variety of areas of the brain, and there are memories which have content in terms of the story of what happened, but then you have memories which are more sensory. So when you walk into your old school and you smell the wood, you can get this almost supernatural sense of being a child again, and I think that's just tapping into what is effectively a sensory memory.
And is that wrapped up with superstition in some way?
Not necessarily, although it does have relevance to this idea that you can have, if you like, intuitive ways of thinking about the world that are operating almost unconsciously, and these are affecting the ways that you're thinking.
Yeah, so I know that I used to do some bits and pieces with in theatre and working on lighting design, and light is a very, very key perceptor, isn't it? It's how light is actually how we perceive the world.
Yes, and the majority of the sensory processing area of the human is dedicated to visual processing.
Yeah. Shall we go to Jim? Is it Jim that will go? Yep. Okay, Jim. Hello.
Hello. Good evening, Nick. Good evening, Doctor.
Hello.
You get bitten by a poisonous snake. The antidote is venom. How does that work?
Well, not quite. The antidote's actually anti-venom. What you do is, a snake, when it bites you, its fangs inject under the skin the venom. And the venom in snakes and scorpions and things that pierce skin is a protein. And that protein circulates in the bloodstream, doing various nasty things. It can attack the clotting cascade, other parts of that protein, that's the thing that clots blood. It can also burst cells and trigger all kinds of nasty inflammatory reactions that make you very, very unwell. So what scientists and doctors do is they collect venom from a snake, or a spider, or a scorpion, and you then dilute it down to quite a low level, and you inject that venom into another animal in very small amounts. Usually you use rabbits, and the rabbits then make antibodies small pieces of protein shaped like a letter Y, which can specifically recognise just that venom molecule. And then what you do, when the rabbit has made very high levels of that antibody in the blood, you collect some of the rabbit's blood, and you then use a very clever biochemical technique, affinity chromatography and affinity separation in a column, and you can collect just the antibody against the venom. It doesn't collect any of the other rabbit antibodies or rabbit proteins, and so you make a concentrated solution just of the antibodies that recognise the venom. And then you put those into a vial and label it, this one treats black widow spiders. And then when a patient comes into hospital and they've been bitten by a black widow spider, the doctor goes to the medicine chest and picks out the one that says anti-venom against black widow spiders and injects that into the patient. And those rabbit antibodies then circulate in your bloodstream, and they lock on specifically to the venom molecules and nothing else, and they neutralise it, because the venom has essentially a business end that does the damage to you, and the antibody blocks that up. So it's rather like you letting down the tyres on someone's car. It can't go along very well anymore. It won't actually be effective as a getaway vehicle. And that's how it works.
There's a lot more to it than me.
Yeah, there certainly is, Jim. Thank you very much indeed for that. Just one on, just a quick one on the text that's just dropped in for our sports engineer specialist that we've got with us. How does Lycra make blokes run faster?
They're scared to be seen dead in it.
That's right. Yeah, it certainly would make me run faster, that's for sure. There are two things. One is aerodynamics. That, you know, if you're a cyclist or if you're studying a speed sprinter, then the hairs on your leg will slow you down and give you drag force. So put Lycra on, or if you're a dedicated athlete, shave those hairs off, then you'll go faster. But there is also the fact that it can help compress muscles and make muscles function a little bit more efficiently as well. So you've got two factors, but aerodynamics is certainly the first one that comes to mind.
OK, following on from that then, here's a supplementary for you for your three bonus questions. 3 bonus points, should I say. If you've got a swimmer, right, who's wearing these suits, you know, these swimming suits that you get?
Yeah, the fast skin or shark skin type suits that Ian Thorpe made very popular, yeah.
How can they make you go faster than actual skin?
Well, they're mimicking skin, but in this case they're mimicking the skin of a shark. And the skin of the shark has very, very small V-shape little bumps on them, and it's to do with fluid dynamics, to how the water flows over the body. So you mimic a shark skin, which is extremely efficient, much more efficient than the human skin, because we're not designed to swim through the water at very high speeds, and it allows the water to flow more efficiently across the body. It minimises what we call the dead zone, the water that just sits on the small of the back and that basically presses you down into the water, which you don't want. You want to go forward, you want minimum weight to go forwards, and it therefore helps the swimmers and the athletes minimise their drag and go faster.
So how you know, if you're doing like, I don't know, a 200-metre race, how many seconds is it going to knock off your time if you're wearing one of these shark skin affairs?
It won't take seconds. It's more likely to be milliseconds.
Oh my word!
But in elite performance in the Olympic Games, those milliseconds are enough to mean the difference between gold medal and, say, 4th place.
I tell you what, if I bought one of them and I only knocked milliseconds off my time over 200 metres in the pool, I'd be gutted.
Oh, but you're bound to look good.
Clearly. Laurie's on the line. Hello, Laurie.
Hello, that was rather interesting, hearing about the shark skin.
Yeah, go and buy one tomorrow. It'd be great.
Yeah, what I wondered, I wasn't really listening to the programme when it was on yesterday. I was doing something else, and I didn't get the recipe for your lava lamp, which I thought sounded rather the fun sort of thing that would amuse my grandson.
Shame on you. We're not going to give it to you as a punishment for not listening to our programme.
So thanks for calling in, Laurie.
Oh, we had it on.
Dave, you're going to put this guy out of his misery?
It's quite easy to do. All you do is you put a centimetre or two of water in the bottom of a jam jar or a pint glass. If you colour it with something, it'll look better. Add a load of cooking oil on the top of it and chuck in one of those fizzy tablets, a fizzy vitamin C tablet or an Alka-Seltz or something like that. You get loads of foam produced. It floats
Not
up.
an E.
Cheers, Chris.
How much oil do you put in?
Probably about 10 centimetres. The more oil you put on, the bigger the lava lamp effect will be.
Yeah. just any old kitchen oil.
Yeah.
So hang on a minute. So we put a couple of centimetres of water, colour it up a bit.
Yeah.
Put some oil in.
Chuck 10 centimetres. Fill the rest of the glass up with oil. Put a fizzy tablet in. The tablet will fizz, produce gas, and so you get a foam, and the foam's lighter than the oil, so it will float up to the top. And when it gets to the top, in what is sort of a lava-lampy bubble, because oil and water don't mix, and when it gets to the top, all the bubbles will burst, and all you get left is the water in the foam, which will then sink in another lava-lampy bubble, which goes down again, and you get quite a nice effect.
Very 1970s.
Oh no, just amazing. Laurie, I hope that's made you a happy man.
Yeah, lovely. Yeah. Okay, thanks very much. Yeah, I wasn't sure about the quantities or what the tablets were that you put in there.
Oh, anything that fizzes, apparently.
Live from Norwich with the best of the fest, the Naked Scientists.